In this example here, we want to test whether two genetic traits, for example, color and sex of a population of butterflies, are actually linked with each other. And this linkage could happen, for example, if the genes or the alleles for the particular trait, color and sex, are on the closely linked on a chromosome, for example. So here we've got some observations. We look at some butterflies. We've got 75 male butterflies that are red and 97 that are blue. And we also have 30 female that are red and 58 that are blue. And we want to know whether sex and color are somehow linked to each other. So what do we need to do? First of all, it's always good to formulate a null hypothesis. And we can do that very easily. So we can say, for example, a null hypothesis, a valid null hypothesis would be if we said the two traits that we are looking at, the two traits are independent of each other, independent of each other, and there is no relationship, between the two traits, between color and sex. And any differences that we observe here between our results and expected data are just simply down to sampling error. So let's write that down. Any differences between expected data, that is, if there is no relationship, if they are independent from each other, so independent, if that's independent, and the observed data these are just simply down to sampling error. So that's caused by sampling error. That is our null hypothesis, and of course we can formulate an alternative hypothesis where we basically just simply say the two traits are not independent, and I just simply write that as not independent from each other. There is a relationship between color and sex. So a relationship between color and sex. And any differences that we see between the observed and the expected data are caused, any differences, let's write that down, differences are due to sampling error, because sampling error we always have, are due to sampling error and the linkage between the two traits. And of course, this is now a set of null and alternative hypotheses which we can test. We would usually set a significance level alpha, and very common we would set this to 5%, which is the same as 0.05, and we would make a decision rule. We would calculate a p-value. So we calculate a p-value, and remember, the p-value is the probability that we observe a particular test score if the null hypothesis is correct. And we say if the p-value is smaller than our significance level alpha, that would let us to reject the null hypothesis. And remember the phrase here, if p is low, i.e. lower than alpha, if p is low, h naught must go. If p is higher than alpha, we would fail to reject. P is larger than alpha, we fail to reject. Fail to reject the null hypothesis. Reject the null hypothesis. So we would believe the null hypothesis is true. In the case p is smaller than alpha, we would reject the null hypothesis and therefore accept the alternative hypothesis. So that is our setup for this particular example here. And now we need to calculate what we mean by the expected observations. Now, in order to calculate expected values, we first need to determine marginal values for our observations. And that is pretty straightforward, because all we need to do is we need to calculate the sum of the column values and the sum of the row values. So here we've got 75 and 97. That gives us 172. So I just simply add them up. 58 add 30, that gives us 88. Here we've got, in this row, we've got 105. And here we have 97 add 58, that gives us 155, and the grand total would be 260. So these are the marginal values for this, what is called a contingency table. Now, in the next step, we need to calculate the expected values if the two traits were independent of each other, and for this we use these marginal values that we just calculated. And what we can do is we can just simply take this value, multiply it with this value, and divide it by the grand total to give us this value here. So we would, for this cell here, we would do this calculation basically. I symbolize it like that. So that would be 75 times, that would be, get rid of this, 172 times 105 divided by the grand total 260. For the female equivalent, we would use this value. So we would use 88 times 105 divided by the grand total 260. For the blue data, we would use 172 times 155. So we've got, for this cell here, we use 172, and this row total, 155, divided by 260. And the last one, the female blues, that would be 88 times 155 divided by 260. And these numbers would give us the expected values. In the next step, now we need to calculate our test statistic, and for this we will use a chi-square statistic, which I abbreviate with this sign here, chi-square. And what we are looking at is this equation here. We sum up the differences between the observed minus the expected data, square it and divide it by the expected number here. Okay, so that looks a little bit intimidating, but it's not as bad as it looks like. So basically we start with the first cell here, the red and male, and we calculate 75, that's our observation, minus the expected 69.5 squared divided by the expected number 69.5. And we do the female here, so we have 30 minus the expected, that is 35.5 squared divided by expected, that is 35.5, plus the next one, that is 97, that's the male one again. Observed 97 minus 102.5 squared divided by expected 102.5, plus the last one, that is 58 minus 52.5 squared divided by 52.5. And that is basically our test statistic, and we can put that into a calculator, or since we're in Excel, we can already easily calculate that in Excel. Now if we put this together, we get a chi-square value of 2.1886, if I've done everything right. Now that is our test score, and we now have to convert that into a p-value, and we can do that in Excel with the function of chi-square dist, right distribution. So equals chi-square dist right distribution, and for that we need two parameters. We need our chi-square value, that is the value that we just calculated, that is 2.1886, and we need to figure out the number of degrees of freedom, and in this case we've got 1 degree of freedom. Let's quickly do this calculation. And I made a mistake here. That should be a dot. And this would be our p-value. What is the degrees of freedom? Well, for such a 2x2 contingency table, the degrees of freedom is the number of rows minus 1 multiplied by the number of columns minus 1. So we've got 2 rows, 2 minus 1 times 2 minus 1 columns. So that's 1 times 1. So we've got 1 degree of freedom. Okay, so we've got a p-value of 0.139. So p equals 0.139. And now we need to go back to our decision, and we say with a p-value of 0.139, it is certainly larger than our alpha of our 0.05, and therefore, as it states in our decision rule, we fail to reject the null hypothesis. Fail to reject the null hypothesis. Or in other words, we believe that the null hypothesis is correct. That means the two traits are actually independent of each other. So in this case, sex and color are independent of each other, and they are not linked, not in any way linked to each other. So this is how we can perform a chi-square test for independence with a simple example where we just simply calculate the marginal values of the observed data, compare it to the expected data, and then make a decision from the p-value whether or not we should reject or fail to reject the null hypothesis. I hope this makes sense, and thank you very much for watching.